Hello and welcome to page 5. This is the puzzle page, and here they're given a good amount of information, definitely enough information to figure out the structures of 1, 2, 3, 4, 5 different unknowns. And we're going to just take our time, take a nice deep breath, and then figure out what's going on here. So we're going to elucidate the structures of those 5 compounds. And we're going to first start with unknown A. This has a molecular formula of C6H8. Right there, we stop. And we want to find the degrees of unsaturation. What we're going to compare it to, for unknown A, we're going to compare it to a fully saturated compound where we have 6 hydrogens. We're going to use the formula H2N plus 10. So 6 times 2 is 12, plus 2 is 14. So that's fully saturated. Now the difference between the 14 hydrogens and the 8 hydrogens in this molecule is pretty substantial. 14 minus 8 is 6. So we have 3 pairs of missing hydrogens. We have 3 degrees of unsaturation. All right. So we're going to move on and see that this reacts with 2 molar equivalents of hydrogen with palladium catalyst to give unknown B. So we see that the degrees of unsaturation in unknown B are now 1 degree. We know that 2 of those degrees of unsaturation had to do with or included alkenes. And that was enough, 2 degrees of unsaturation would be 2 alkenes or 1 alkyne. So we kind of need to see what happens later on in the molecule. We can see that this 1 degree of unsaturation then must be a ring because it's not a pi bond because it wasn't absorbed by palladium and hydrogen. So to recap, we know that unknown A has 2 pi bonds and 1 ring. We know that unknown B just has the 1 ring. We start in the next paragraph. New thing, treatment of A with ozone, followed by zinc, meant to leave a little highlight. Treatment of A with zinc with ozone, we have 2 equivalents of the same product C. So what that tells us is actually a pretty good piece of information that we have 2 equivalents of the same product C. So that must mean that A is symmetric if we got 2 of the same compounds. We went from a C6 compound to a C3 compound. Even better, they tell you that unknown C is a symmetric dialdehyde, contains 2 aldehydes, with this molecular formula. If you remember your rules for calculating degrees of unsaturation, you'll remember that you'll ignore oxygen. So the hydrocarbon equivalent of this is actually C3H4, and that's going to help us to determine the number of degrees of unsaturation in unknown C if there's anything besides those aldehydes. We compare it to the fully saturated form, C3H8. We see that there is just 2 degrees of unsaturation then, if we took the difference between the 8 in the fully saturated form and the 4 in the actual compound. So those 2 degrees of unsaturation are explained by the 2 aldehydes, and that's it. Now, this is a really good point to start drawing a substructure because it's only 3 carbons. And if we just do this 1, 2, 3 chain, and we know that aldehydes have to be at the end of the chain, then this is the structure of unknown C. This is the only thing that it could be, and this is going to be super, super key for us. So we have 2 unknown C's, and actually, in order for you to see this, I'm going to move some stuff around. Let me just pause it. Okay, so what I did here is I drew the structure of unknown C twice, and I did it in such a way that the 2 carbonyls were facing each other or lined up, because that's how oxidative cleavage works. We know that in ozonolysis particularly, that we're going to be cleaving the carbon-carbon sigma and pi bond entirely, and wherever the alkene carbons were, this is where the aldehyde carbons will end up. So that means that I could go ahead and just do a little trick here, or I could move this guy over here. This isn't going to look super pretty to start, but if I just sort of erase these oxygens, and put in between those two just double bonds, then this is the messy version of our structure where we have alkenes in between these 4 carbons. So that's the messy version. Let me clean it up. What it really is, the 2 double bonds, they're on either side. So this does go along with it being a symmetric molecule. And this would split into ozone, or sorry, it would be split by ozone into those 2 dialdehydes. This is once again super, super key for us. We can work our way backwards before you move your way forwards to really apply that. Since we know that unknown A is this structure here, oops. We know that if it went under catalytic hydrogenation with 2 equivalents, that the 1 ring would be the cyclohexane. So we already know A, we already know B. We'll copy those down there at the bottom. But now we'll do one more copy, unknown A, and we see that it reacts with 2 equivalents of osmium tetroxide. We have 2 stereoisomeric products, and they both have the formula C6H12O4. This has 1 degree of unsaturation, has 4 oxygens. If you remember that adding osmium is actually a dihydroxylation, so these compounds are going to make, this reaction is going to make thin diols, but since there's 2 alkenes to start, we're going to have 2 diols, and that's a total of 4 alcohols. So there's going to be just 2 different, many different possibilities here of the different ways that you could draw them. But the first thought would be, since it's a syn hydroxylation, to put all 4 of those alcohol groups on all 4 of those carbons all on the same side. So wherever we have alkene carbons, those 2 are going to be alcohols. And then we have another set of alkene carbons here on this side. So we have cis alcohols here. Now the question is, are these alcohols, this set of alcohols, are they cis to each other? In this case, yes, they are. But they also could have been trans to each other. As I'm figuring out how to come up with the other stereoisomer, I then consider, well, what if those 2 syn diol groups were actually added to opposite sides of the ring, and these 2 groups were actually trans to each other, but still when you have the 1-2 relationship, those diols from osmium tetroxide, those have to be syn. And by that, just to be very clear, these are syn, these are syn, these are syn, and I'll just circle it as are those. So that's the structures of all those compounds. Just to finish this up, you would transcribe those into the bottom boxes, but I don't think I'm going to do that because you can see what all of the structures are. I hope that was helpful.